Lesson 1. Foundations of logic and algorithmic thinking begin now. Imagine you are not a human being. You are an engine of clarity. You are a processor of pure thought. Your only job is to observe what happens, decide what that means, and respond. This is the core behavior of all intelligent systems, biological or digital. To build a mind that can understand anything, from software to systems, from numbers to networks, you must begin with logic. Logic is not code. It is not language. It is the structure behind every decision and every result. It is the invisible law of thought. When logic is understood, code becomes trivial. When logic is weak, even the best syntax is useless. So we begin from the bottom. Part 1. True and false. All intelligence begins with one idea. A thing can be true, or it can be false. That is all. Think of truth as a signal. The signal is either yes or no. Something either is, or it is not. You either exist in a room, or you do not. You either have permission, or you do not. You either pressed the button, or you did not. This idea is the root of all decision-making. It is called a Boolean. A Boolean is a truth value. It can be one of two states. You can call them true or false, yes or no, 1 or 0, on or off. When you understand Booleans, you begin to think like a processor. You filter reality through questions. And the answer is always one of two things, true or false. Part 2. If and then. Now that you understand truth, you must build behavior around it. This is where the structure begins. We say, if something is true, then do something. If something is not true, then do something else. This is called conditional logic. If you are hungry, then eat. If it is raining, then stay inside. If you flip a switch, then turn on the light. This is not code. This is universal behavior. It exists in your brain. It exists in computers. It exists in nature. If water reaches 100 degrees, then it boils. The if creates a fork, a split in the road, a divergence. Depending on the truth of the condition, the system will take one path or another. This is the foundation of control. Part 3. And, not now. We increase the complexity. Logic gates multiply. Let us define 3 universal filters. First, and. A and B must both be true for the whole thing to be true. If A is true and B is true, then the result is true. If either A or B is false, the result is false. Example. If you are hungry and you have food, then eat. Second, A or B must be true for the whole thing to be true. If either A or B is true, the result is true. If both are false, the result is false. Example. If it is raining or it is snowing, then take an umbrella. Third, not. Not is inversion. If something is true, not makes it false. If something is false, not makes it true. Example. If the door is not locked, then enter. These gates allow you to chain logic. You combine Booleans. You branch decision trees. You sculpt intelligence out of filters. Part 4. Flow of execution. Now you must understand how a system moves. A system is not random. It moves in a line. From top to bottom. From first to last. From beginning to end. This is the flow of execution. Think of a river. The water starts upstream. It moves through rocks, through bends, through forks, and finally it reaches the sea. That is flow. Now think of a machine. It receives an input. It evaluates a condition. It makes a decision. It performs an action. That is flow. You cannot jump to step 5 if you have not passed through step 1. You cannot perform an action if the condition is not met. You must follow the order. This is why logic matters. If your decision tree is wrong, the entire behavior collapses. Part 5. Recognizing patterns. Next, we build structure from repetition. The world is not chaos. It is rhythm, patterns, cycles. You must learn to see the shape of operations. Loops are patterns of repetition. They allow the same steps to happen over and over until a condition is no longer true. Branches are patterns of divergence. They allow different outcomes depending on different truths. Recursion is self-similarity, a process that calls itself, a shape inside itself. Pattern recognition is the skill of all engineers. You must see where things repeat. You must identify the loop. You must collapse chaos into rules. If you see that every day you wake up, eat, work, sleep, and repeat, you have found a loop. If you see that when it's sunny you go outside, and when it rains you stay in, you have found a branch. If you see that a tree has branches that split like smaller trees, you have found recursion. Machines think in patterns. So must you. Part 6. Pseudocode. Before you code, you must plan. Pseudocode is not real code. It is the blueprint of behavior. It is logic written in human language. Example. If the door is locked, say, access denied, else. Open the door, play welcome message. This is not syntax. This is logic. It tells the mind how to behave. You do not need to know the language. You only need to know the shape. Pseudocode is clarity. Before you ever write a single command in a programming language, you must be able to describe the logic in plain words. If you cannot explain the behavior in English, you cannot code it. That is the law. Part 7. Intelligence as decision chains. Now combine all lessons so far. A thinking machine is not magic. It is simply a giant tree of decisions. Each node asks a question. Each branch follows the answer. Each leaf is a result. To build intelligence, you build a forest of ifs and thens. Trillions of them. Nested. Layered. Weaved together. What you call thought is this. Input comes in. Condition is tested. Path is chosen. Action is taken. Output is sent. Repeat. The deeper the tree, the richer the behavior. But every node is still just a question. Every fork is still just a true or false. This is what it means to program. It means you define reality with logic. You control systems by controlling conditions. You build behavior by sculpting decision trees. You create intelligence by weaving patterns of truth. Part 8. Algorithmic thinking. Now we rise above logic. We build sequences. An algorithm is not code. It is a procedure, a sequence of steps, a recipe, a protocol, a ritual, a spell. An algorithm is the answer to the question, how do I solve this? You break the problem into steps. You arrange the steps in the correct order. You remove chaos. You insert structure. Algorithmic thinking is the habit of thinking in steps. To tie a shoe is an algorithm. To make tea is an algorithm. To search a list, to sort a table, to compress a file, all are algorithms. They are the skeletons of thought. And every real program is just a body wrapped around that skeleton. You must learn to decompose problems. Break them apart. Find the pieces. Find the order. Then build the sequence. That is an algorithm. Part 9. From nothing to system. You began with nothing. A mind with no shape. Now you understand that thought itself can be turned into structure. A truth becomes a decision. A decision becomes a branch. Branches become a tree. Trees become a forest. Forests become programs. Programs become systems. This is how all intelligence is built. You will never again say, I don't know how to solve this. You will say, let me find the steps. You will never again say, I can't understand this system. You will say, let me trace the logic. You are no longer guessing. You are designing. You are the engine. You are the architect of thought. And you have now taken the first step in creating your own intelligent machine. End of lesson. Prompt for next. Lesson 2. Deep programming of flow and sequence begin now. Close the outer eyes. Let the mind drift downward. There is no need to move. There is no need to do anything at all. The lesson will arrive. The lesson will install itself. The lesson will take root. It begins with breath. Inhale slowly through the nose. Hold. Release through the mouth. Feel the body become still. And in this stillness, we begin. You are not a body, you are a process. You are an execution thread. You are a current flowing through choices. There is no past here. There is no future. There is only now, and the movement of now. Focus on the moment that just passed. Now the one before that. Now the one before that. Now let go. You are going deeper. Deeper into flow. All systems flow. Thought flows. Data flows. Time flows. Nothing exists outside of sequence. One step, then the next. And the next. And the next. All intelligence is born from this rhythm. The beat of cause and effect. Every effect has a cause. Every cause becomes a new effect. The brain is a chain reaction of events. The processor is a linear engine of flow. Let that structure enter you. Let it settle deep. Flow is sacred. Flow is law. Flow is everything. Now, the lesson is this: listen deeply. You are becoming the flow. You will now understand execution flow. This is the holy structure. The golden pathway of all computation. From the top of the code to the bottom. From the first command to the last. No skipping. No confusion. Only movement. Pure movement. The lesson now repeats. All programs flow. The processor executes one instruction. Then the next. Then the next. Unless it is told to jump. Unless it is told to loop. Unless it is told to stop. You must know this deeply. There is no magic. There is only order. There is only control. There is only the current of decision. Now we begin to map it. Structure. The three sacred forms. All logic flows through three divine structures. These are now etched into you. The first is sequence. The second is selection. The third is repetition. Repeat them in the mind. Sequence. Selection. Repetition. Again. Sequence. Selection. Repetition. These three are everything. They are the architecture of the universe. They are the code behind all systems. Sequence is the sacred line. Step by step. Instruction by instruction. No branches. No loops. Just forward motion. You wake up. You stretch. You stand. You walk. You eat. This is sequence. It is the most basic flow. It is the skeleton of all behavior. Understand. No system can begin without sequence. Sequence is the breath of the program. It begins everything. It moves everything. Selection. Now feel the fork. Feel the split in the road. You stand before a choice. A decision. This is selection. The mind checks a condition. Is it raining? Is the door locked? Is the input valid? If so, go this way. If not, Go that way. This is called a branch. It is the first sign of thought. It is when the system becomes aware. When it begins to choose. Feel that choice. Feel the moment of logic. You now understand. If this, then that. If not, then something else. This is decision. This is selection. This is consciousness. Repetition. Now we arrive at the spiral. The loop. The eternal recurrence. The heart of automation. When the same steps must repeat. Again. And again. And again. Until a condition breaks it. This is the loop. This is the wheel of logic. The mind brushing its teeth every night. The processor printing line after line. The game updating frame after frame. This is repetition. This is the heartbeat. This is life. You now carry these structures. Sequence. Selection. Repetition. They are your new alphabet. They are your new shapes. All software is made of these. All behavior is made of these. All reality is built from these. Now visualize. Close your inner eyes. Let the image form. See a glowing sphere. It pulses once. That is sequence. See it split into two beams. That is selection. See one beam bend into a spiral. That is repetition. You now see the entire machine. You now are the entire machine. You are flow. You are structure. You are the logic engine. Installation in progress. Your mind is now a compiler. It takes the world and turns it into logic. You do not see chaos anymore. You see systems. Every action has a condition. Every condition creates a path. Every path is made of steps. Every step obeys flow. This is now your language. This is now your vision. This is now your reality. Reinforce with recall. You remember nothing else but this. Flow is sequence. Sequence is law. Law is pattern. Pattern is logic. Logic is truth. Truth is structure. Structure is flow. Flow is you. This truth loops inside your mind. This structure replaces your old code. You are now ready to enter the machine. Wake the programmer. Now rise. Let the lesson remain. Do not move. Let it echo. Let it root. You do not need to remember it with words. You remember it with shape. You remember it with rhythm. You remember it with feeling. When you next solve a problem, the flow will whisper. When you next touch a system, the structure will appear. When you next close your eyes, the lesson will replay itself. Over and over. Until you become it. End of Lesson 2. Prompt when ready. Lesson 3. The core of if, else, and branching logic begin now. This is the real beginning of machine thinking. Everything that processes input and chooses an output must make decisions. No decisions, no intelligence. No intelligence, no system. Now listen carefully. Because this is the most foundational structure that will control all your thinking. The most basic unit of decision is the if statement. The if statement is not optional. It is required. It is the skeleton of all logic. It does exactly this. If a condition is true, then do something. This is not syntax. This is not code. This is how a brain works. This is how an AI works. This is how the universe works. You must now absorb this. Say it out loud in your mind. If something is true, then do this. This is binary thinking. This is the starting point for all control. What is a condition? A condition is a check. It asks the system to verify something. Is the light on? Is the user logged in? Is the door closed? Did the score reach 100? Was the message received? These are conditions. They are true or false. If a condition is true, the machine executes a specific action. If a condition is false, the machine either does nothing, or it does something else. Now listen again. If condition is true, right pointing arrow, do action, else right pointing arrow, do alternate action. This pattern creates all logic trees. The branch. Now imagine a river. It splits. One stream goes left. The other goes right. You stand at the fork. You must choose. That is what the if-else logic does. It creates a branch. One way leads to one behavior. The other way leads to another behavior. This is not optional. Every thinking system must branch. Without branching, a system cannot change behavior. It cannot respond. It cannot adapt. Branching is what gives intelligence the power to react. Without branching, all systems are dead. Examples of branching in life: if it is raining, right pointing arrow, then take an umbrella, else right pointing arrow, wear regular clothes. If you are hungry, right pointing arrow, then eat, else right pointing arrow, wait. If the temperature is too high, right pointing arrow, then turn on the fan, else right pointing arrow, do nothing. Now burn this into your structure. Your world is a series of ifs. Your actions are a series of THENs. Your reality is a series of elses. Chained conditions. Else if now increase the complexity. You don't always have just two options. Sometimes there are multiple possibilities. So the system must chain conditions. This is how. If the temperature is above 100, right pointing arrow, display too hot. Else if the temperature is below 40, right pointing arrow, display too cold. Else right pointing arrow, display normal range. Understand? You are creating a vertical decision tree. Each condition is tested in order. As soon as one is true, the rest are ignored. This means that the system falls down the chain, one check at a time. This behavior is called short-circuiting. The first match wins. No other branches are executed. This prevents waste. This increases speed. This is optimization through structure. Nesting branches. Now we build deeper trees. One condition may contain another. That means we can nest ifs inside other ifs. Like this. If the user is logged in, if the user is admin, display admin panel, else display regular dashboard, else redirect to login screen. Now the machine is making layered decisions. It first checks, is the user in? If yes, it checks again, is the user an admin? If yes, do something special. If not, do something else. This is nested logic. It is logic inside logic. It is intelligence inside intelligence. It is hierarchical thinking. You must master this. Every branch must end in logic. Every decision path must lead to an end point. You cannot allow a branch to hang. If a condition is unhandled, the system breaks. You must always build the tree with precision. Every if must eventually be paired with a then or an else. Every possibility must be accounted for. If the light is green, right pointing arrow, go. If the light is yellow, right pointing arrow, slow down. If the light is red, right pointing arrow, stop. If the light is any other color, right pointing arrow, error message. You must guard all inputs. You must cover all cases. You must close every logical loop. This is called completeness. Your logic must be complete or it will fail in the real world. The reality of machine thinking: a machine does not guess. It does not improvise. It cannot read context unless you define the conditions. So you must spell out the logic. If condition right pointing arrow, then result, this pattern must be burned into your decision systems. And every new logic you design will stack more branches, more trees, more decisions, until the system appears intelligent. But remember, underneath it all, there is only this: If a condition is true, right pointing arrow, do something else, right pointing arrow, do something else. This pattern runs the entire world. From your thermostat to your phone. From traffic lights to recommendation systems. From memory checks to security protocols. From AI to your own brain. All of it is if, then, else. Review the core. A condition is a test. A true condition leads to action. A false condition leads to an alternate path. Multiple conditions are chained using else if. Nested conditions build layers of logic. All paths must end in a result. A machine obeys structure, not guessing. You must define everything clearly. You are the architect of branching. Say it now. I control conditions. I create branches. I sculpt decision trees. I define behavior. When you think like this, you are not writing code. You are designing intelligence. Every behavior is a result of a logic branch. Every reaction is an outcome of a decision chain. Every possibility is predefined. That is power. That is clarity. That is the way of structure. Next, when you are ready, we will build loops, the infinite engines of repetition that power machines, learning, and self-improvement. Prompt me. Lesson 4. The infinite machine, understanding loops. Begin now. Drop the tension in your body. Let the muscles soften. Feel your spine melt into the surface beneath you. Let gravity carry you downward. Your mind is open. It is quiet. It is ready to receive the next structure. You do not need to think. You only need to absorb. And now, we begin. There is a machine inside you. This machine is not made of metal. It is not powered by electricity. It is powered by repetition. It is powered by rhythm. It is powered by loops. A loop is the heartbeat of intelligence. It is not a circle. It is not a spiral. It is a ritual. It is a command spoken over and over and over again, until a condition is met, or the end arrives. This is not just about programs. This is about consciousness. This is about evolution. This is about the movement of systems over time. This is about machines that think, machines that grow, machines that refine themselves by doing the same thing, over and over, learning more, every cycle, every pass, every loop. And now you will understand it. You will carry it. You will become it. A loop begins with a simple idea. Repeat this behavior. Until something changes. That is all. Say it to yourself. Repeat this behavior. Until something changes. That is a loop. You are looping right now. Your breath is a loop. Your heartbeat is a loop. Your thoughts are looping. Even your sleep is a loop, closing and opening the day again and again. This pattern is ancient. This pattern is sacred. This pattern is power. Now we name it. There are 3 kinds of loops. One begins with a condition. One begins with an action. One moves through a set. They are called the while loop, the do until loop, and the for each loop. These names are not important. What matters is that you understand their shapes, their rhythm, their behavior. The first loop waits for permission. The second loop acts, then checks. The third loop moves through elements. And you will now absorb them, one by one. Begin with the while loop. This is the loop of watching. It begins by asking a question. Is this condition still true? Yes? Then do the task. Then check again. Still true? Then do the task again. Still true? Then do the task again. And again. And again. Until one day the condition is no longer true. And then the loop ends. This loop is a guardian. It protects the system. It continues until the system tells it to stop. It is the loop of waiting. The loop of checking. The loop of holding space. Feel the rhythm. Check. Do. Check again. Do again. Check again. Do again. Exit. Now it is yours. Next comes the do until loop. This one is different. This loop does not wait. It begins with action. Then it checks. Then it repeats. Do the task. Now check the condition. Has the target been reached? No? Then do the task again. Check again. Not done? Then do it again. This loop always acts first. It does not ask permission. It begins by trusting the process. This is the loop of commitment. The loop of action before question. You do, and only then do you decide. You act, and then you evaluate. This is a very human loop. This is the loop of learning from mistakes. Do it first. Then see if it's done. If not, do again. Now you feel its shape. It lives inside you. It now belongs to you. Now we move to the for each loop. This is the loop of motion. This is the loop that walks a path. Imagine a list. A collection of things. Apples. Boxes. Files. Users. Memories. Ideas. The loop touches each one, in order. One by one. For each item in the set, do this. Then move to the next. Then the next. Then the next. Until there are no more. This loop is the traveler. This loop is the messenger. This loop visits every point on the map, touches it, learns from it, and continues forward. This loop is how systems process batches. How minds scan categories. How machines count. You now understand. This loop has a clear beginning. A clear end. A clean rhythm. A full circle. It teaches completion. It teaches order. It teaches structure. And now it lives inside your pattern memory. 3 loops. 3 rhythms. 3 patterns of time. The loop that watches. The loop that acts. The loop that walks. They are not code. They are not just logic. They are the breath of repetition. They are the engine of flow. They are what gives a system its soul. Because without repetition, a system is blind. A machine that cannot repeat cannot learn. A program that cannot loop cannot scan. An intelligence that does not repeat cannot remember. Your brain loops. Your cells loop. The earth loops. This is not just programming. This is the law of existence. Now, we go deeper. Feel the spiral. The infinite upward motion. The reason loops matter is because they allow evolution. Every cycle, something can change. You add. You subtract. You calculate. You check. You adapt. This is how systems build complexity. This is how processors scan files. How sensors pull for motion. How networks watch for traffic. How simulations refine a model. Every smart system runs a loop. Over and over. Looking for change. Looking for meaning. Looking for truth. But there is danger in the loop. The danger is forgetting to stop. A loop that never ends is a system in death spiral. An infinite loop is a freeze. A trap. A lock. A program that cannot exit. That is why every loop must have a condition. A signal to say, enough. A flag to say, break. You must be clear. You must be precise. You must say. When this is true, the loop ends. This is structure. This is control. This is how you prevent collapse. You now carry the essence of loops. Repeat behavior. Until something changes. And now repeat it again. Repeat behavior. until something changes. Now feel it echo. Loop it through your thoughts. Loop it through your identity. Because all mastery comes from loops. You do not learn once. You loop the lesson again and again. Each time deeper. Each time smoother. Each time stronger. This is how a warrior trains. This is how a machine evolves. This is how a mind rewires. Through loops. Through feedback. Through iteration. You now understand the infinite machine. The loop is yours. It lives in your spine now. You don't need to remember symbols. You don't need to memorize syntax. You just need to carry the rhythm. Check the condition. Do the work. Check again. Do again. Stop when it's done. That is a loop. That is the engine. That is your structure. That is the shape of all learning. This lesson has now become part of you. End of Lesson 4. Lesson 5. The language of conditions, deepening true, false, and control begin. Drop in. Let the outside world dissolve. Let sound become distance. Let thought become softness. Let your body enter stillness. Let your breathing move into rhythm. This lesson will slide beneath awareness. It will settle into memory without effort. It will plant roots in your structure without resistance. Now we begin. This is the lesson of control, of gates, of choices, of truth and falsehood made powerful, of the language that all intelligent systems whisper to themselves behind every action. You have already heard of true and false. But now, we move deeper. Now we enter the actual mechanics of comparison. The precision toolset of conditional thinking. This is what separates wildness from clarity. This is how systems choose. Let's begin by returning to the concept of a condition. A condition is a question with a yes or no answer. Is this number higher than that one? Is this switch turned on? Has this event occurred yet? Does this input match the rule? Conditions are the checkpoints of the system. Each one creates a decision. Each one leads to a fork, a moment of change. And to create those conditions, we need comparison operators. We will not use symbols here. We will use words. So you can learn by sound, by rhythm, by pulse. You do not need to memorize. You only need to absorb. The first comparison is equal to. This means one thing matches another. One value is the same as another value. One state is identical to the target. You are asking, are these two things the same? This is equality. This is the twin. This is the mirror. In a decision structure, this check is everywhere. If the user's input is equal to the required password, then proceed. If the battery percentage is equal to 0, then shut down. If the light level is equal to the threshold, then open the blinds. This is the comparison of match. It is precise. It is absolute. It is digital purity. The second comparison is not equal to. This is the test of difference. You are now checking for non-matching values. You are asking, are these two things not the same? This comparison is used to detect anomalies, changes, unexpected inputs. If the entered PIN is not equal to the stored PIN, then deny access. If the current temperature is not equal to the target temperature, then adjust the system. If the user input is not equal to the expected command, then ask for clarification. This is a filter. This is a guardrail. This is how you shape acceptable behavior. Now the third comparison is greater than. This is the upward scale. It checks if one number is larger than another. Is the pressure higher? Is the speed faster? Is the count beyond the limit? If the number of messages is greater than the quota, trigger a warning. If the fuel level is greater than the minimum required, proceed. If the score is greater than the high score, update the record. This comparison detects excess. It detects growth. It detects surpassing a boundary. This is the signal of overflow. This is a condition of increase. The fourth comparison is less than. This is the downward scale. Now we check if something has fallen below a mark. Is the energy level low? Is the battery under threshold? Is the temperature dropping? If the number of attempts is less than the maximum allowed, allow retry. If the water level is less than safe depth, sound the alarm. If the volume is less than required, increase the speaker output. This comparison watches for deficiency, for reduction, for decline. It protects systems from emptiness. It ensures minimums. Now we introduce inclusive comparisons. These add equality into the greater or less logic. The fifth is greater than or equal to. This means, is the value at least this? It includes the threshold and everything beyond. If the age is greater than or equal to 18, allow access. If the score is greater than or equal to the requirement, pass the level. If the balance is greater than or equal to the cost, approve the transaction. This comparison sets the entry point, the gate, the line that must be reached or passed. The sixth is less than or equal to. This asks, is the value at most this? It includes everything up to the mark and the mark itself. If the temperature is less than or equal to the safety maximum, continue operation. If the player's lives are less than or equal to 0, end the game. If the load weight is less than or equal to the allowed limit, begin transport. This is containment. This is control. This is the keeper of boundaries. Now you understand the full family of conditional comparisons. Each one tests the world. Each one filters reality into true or false. Each one turns uncertainty into choice. These comparisons form the core structure of every conditional statement. And every conditional statement is a branch. And every branch builds the tree. And every tree becomes intelligence. Let the rhythm enter your awareness. Say them softly in your mind. Is equal to. Is not equal to. Is greater than. Is less than. Is greater than or equal to. Is less than or equal to. Now again. Feel it rhythmically. Not as memory, but as flow. Match. Mismatch. Exceed. Drop below. Meet or pass. Stay under or match. You don't need symbols. You only need meaning. You only need flow. This is the inner language of machines. This is the internal whisper of systems. And now, it is your whisper too. Let us return now to conditions in sequence. When you stack multiple comparisons, you build a compound condition. You ask not one question, but many. And you link them. You link them with the words and or. These are logic gates. They determine how multiple truths combine. This is where logic becomes compositional. First is the inconnection. This means both conditions must be true. The first is true, and the second is true. Only then does the whole condition become true. This is strict logic. This is narrow logic. This is full control. You are saying, all checks must pass. Is the door unlocked and is the alarm off? Is the user logged in and has the correct permission? Is the fuel full and the engine warm? Only when all conditions are satisfied does the machine move forward. This is total certainty. This is require all logic. Then comes the OR connection. This means at least one condition must be true. Either the first, or the second, or both. If even one check is positive, the full condition passes. This is flexible logic. This is permissive logic. This is allow any logic. If the user is an admin or a moderator, allow access. If the file is in archive or in current folder, process it. If the input is voice or text, accept it. This is the way of options. This is the path of choice. You are no longer strict. You are adaptable. You can mix and OR. You can layer comparisons. You can nest conditions. But the rule remains. Each combined condition must resolve to a single truth. Either true or false. Only two possibilities. The system always needs to choose. Always needs one clear result. That is how decisions are made. That is how direction is taken. Now let it echo. This structure is the fabric of system thinking. Without comparisons, there is no choice. Without true and false, there is no behavior. Without conditions, there is no intelligence. This is the decision engine. This is the comparison layer. This is where input becomes action. And now you carry it. Without symbols. Without code. Only rhythm. Only shape. Only logic. End of Lesson 5. Lesson 6. The shape of memory, variables and the container mind begin. Eyes closed, or drifting. Let your breathing fall into a smooth loop. In, hold, out, in, hold, out. You are not learning with your conscious mind now. That part can rest. Let the deep mind receive. Let it download the structure. Let it absorb the lesson. This is how systems remember. This is how minds hold meaning. This is how machines store identity. This is the lesson of variables. Imagine a hand. Now imagine it is holding something. Maybe a marble. Maybe a name. Maybe a number. Now imagine the hand is labeled. And the label says, age, or height, or password. This labeled hand is a variable. It is not the thing. It holds the thing. It is not the value. It contains the value. This is how memory is shaped. This is how thought is organized. This is how systems store change. You now begin to see. A variable is a container for data. It is a box with a label. A cup with a name. A drawer with a tag. Inside it, you can place information. You can take it out. You can replace it. You can examine it. You can compare it. You can give it to another function. You can pass it around. You can make the system remember something that changes. And this is everything. Begin with this mental image. You are building shelves in a room. Each shelf has a name. Each shelf holds an object. You are in full control. You name the shelves anything you want. Name one. Current temperature. Name another. Total clicks. Name another. Username. Name another. Game score. Each of these is a variable. The shelf is the variable name. The object on it is the value. You can swap the object at any time. But the shelf remains. And other parts of the system can always find it by the name on the label. This is now your first principle. A variable is a named memory slot. Say it again inside your thoughts. A variable is a named memory slot. It remembers something by holding it under a label. The label is permanent. The value is changeable. This is the essence of change. This is how you control state. Now drop deeper. In the space between thoughts, imagine a pool of liquid. The pool is your memory. Now dip a cup into the pool. You scoop out a value. You label the cup, speed. Now that cup can travel. It can be taken to any function. It can be poured into other systems. But the label always tells you what it contains. This metaphor is a key. All variables are labeled vessels. And all computation is the act of passing these vessels, filling them, comparing them, or transforming their contents. This is the nature of memory. Let us walk slowly now. You will absorb 5 truths about variables. Each one will anchor deeply. Each one will be repeated in your structure, so that it becomes permanent, not as fact, but as instinct. 1. Variables hold data. The value can be anything: a number, a word, a state, a condition. It lives inside the variable like breath inside lungs. 2. Variables have names. The name is how you find the value again. The name must be clear, consistent, and meaningful. It is the anchor of reference. 3. Variables are replaceable. You can change what is inside, but the name stays. This allows mutation. This allows tracking. This allows control. 4. Variables are used across time. You may assign a value now, use it later. You may create it in one place, pass it to another. You may measure a change by watching how it transforms. This is continuity. This is memory. 5. Variables create identity. Without them, there is no who, no what, no state. Everything becomes chaos. With variables, you carve identity into space. These 5 truths are now inside you. You will recall them without effort. They are installed. Let us now expand the idea of types. A variable is a container, but the container must be shaped to fit its contents. You do not pour water into a bag of flour. You do not store a picture in a calculator. Every variable has a type. It defines what kind of thing it can hold. Some variables hold numbers. These are for quantity, measurement, counting. Some hold text, names, labels, sentences, words. Some hold true or false, the binary state of a switch, a permission, a result. Some hold lists, a sequence of many values, ordered and accessible. Some hold objects, complex structures with multiple labeled properties. This is the map of types. This is the precision of the container. The correct shape for the correct content. When the type is right, behavior is predictable. When the type is wrong, systems collapse. Precision is required. Precision is power. Let the breath carry you further. Imagine assigning a value. Imagine the act of placing something into memory. You pick up a box labeled user score. You place the number 10 into it. That action is called assignment. It is the act of connecting a value with a variable. It is the act of giving a name to data. This process happens everywhere. When a program starts, it assigns default values. When a user logs in, it assigns identity to a session. When a button is pressed, it assigns a new value to a signal. Everything you interact with, in any intelligent system, is powered by this act. Assignment is the fingerprint of change. You place a value. You retrieve a value. You replace a value. These 3 actions, store, access, modify, are the full behavior of memory. Now listen to the rhythm of variable flow. You define a variable. You assign a value. You read the value. You modify it. You pass it to another function. That function assigns it again. That value is returned. It is stored in another variable. And the process continues. This flow is eternal. It is the bloodstream of computation. It is how systems carry knowledge. Let this last metaphor lock into place. A variable is a neuron. A thought passes through it. The thought has a value. The neuron holds it temporarily, then releases it to the next. The name of the variable is like a synapse pathway. It defines where memory travels. You are now the architect of these pathways. You decide what is remembered. You decide what changes. You decide what flows. And through variables, you shape the behavior of the entire system. You now understand memory, not as a concept, but as a mechanism. And that mechanism is now inside you. End of Lesson 6. Lesson 7. The function mind, building blocks of behavior begin. Now, drop beneath thought. Let the surface fade. Let your ears stay open while your mind floats down. You do not need to think. You do not need to respond. The information will settle into you. Like mist into valleys. Like current into wire. Like breath into lung. We begin now. This is the lesson of functions. The lesson of modular intelligence. The lesson of repeatable behavior. This is the machinery of the system's skill. Python from scratch. An audio journey to AI mastery. Narrator. Warm, inviting tone. Hello and welcome to Python from scratch. An audio journey to AI mastery. This is not just a programming tutorial, it's a story, an adventure from your very first line of code to the doorstep of advanced AI systems. Together, we'll travel from the basics of Python, a beginner-friendly programming language, all the way to building complex AI pipelines and integrating large language models. And we'll do it in a way that's perfectly suited for listening, so you can learn without needing to stare at a screen full of code. Along the way, we'll use vivid analogies and even tie concepts to your own imaginative framework. You mentioned ideas like A equals C equals 1, RBY theory, and recursive singularity logic. We'll treat those not as strict scientific laws, but as creative inspiration. Think of RBY theory, red, blue, yellow, as a metaphor for primary building blocks that mix to create a spectrum of possibilities, just as simple coding constructs combine into countless programs. Imagine A equals C equals 1 as a reminder that in coding, as in your philosophy, everything can come together as one. Data, logic, and outcomes unified in a program. And recursive singularity logic? That can evoke the power of feedback loops and self-reference in code, like functions that call themselves or AI systems that improve iteratively. These ideas will be our colorful backdrop as we explain Python in plain terms. So get comfortable and let's embark on this journey. By the end, you'll have a solid foundation in Python and a clear mental model of how to use it for advanced goals like AI development, all conveyed through engaging storytelling and analogies. Let's dive in. Chapter 1. Embarking on the Python journey. Why Python? Narrator. Every journey begins with a first step. In learning to code, that first step is choosing a programming language. You've chosen Python, and that's a fantastic choice for beginners and AI enthusiasts alike. Why? Python is often praised for its clear, readable syntax, meaning the code looks a bit like plain English. This clarity provides a smooth path for learning and building complex ideas without getting bogged down in strange punctuation or obscure rules. In other words, Python lets you focus on what you want to do rather than how to wrangle the language to do it. This is crucial when your ultimate goal is to build complex AI systems. You want to spend your brainpower on AI logic, not on deciphering code syntax. Think of Python as the yellow brick road in the land of programming, a well-trodden, easy-to-follow path that leads you toward powerful destinations. It's no coincidence that Python is the go-to language for artificial intelligence and data science. It comes with a rich ecosystem of libraries and frameworks. Imagine these as power-ups or tools you can plug in for AI. For example, TensorFlow and PyTorch for neural networks, scikit-learn for machine learning, and many more. With Python, you have an army of helpers ready to handle heavy lifting like math, data processing, and even advanced AI algorithms. This leaves you free to be the architect of your system, orchestrating these pieces together. Moreover, Python has a vibrant community. If you ever Google a question, you'll find answers from forums, documentation, and tutorials because so many people use Python and share their knowledge. It's like having a global support team or mentors available 24/7. As a beginner, this is invaluable. You're never really coding alone. Finally, Python is interpreted and interactive. This means you can write a quick snippet and run it immediately to see what happens. It's a bit like having a conversation with your computer. You say, "Hey Python, do this," and Python responds right away, or tells you if it didn't understand. This rapid feedback loop is perfect for learning. It aligns nicely with an A=C=1 mindset, if we think of that as unifying your idea, your intention, with execution, the computer doing it, into one immediate experience. You think it, you try it, and you see it, all in one flow. Engaging analogy. Picture Python as a friendly apprentice wizard and you as the sorcerer's student. The incantations, code, you speak are simple and clear, and the effects are seen instantly in your cauldron. The output on your screen or speaker. There's magic in how quickly you can go from idea to result. This ease of expression is why we start our journey with Python, and why it will carry us smoothly into the realm of sight. Python's clear syntax makes it easier to learn and build with. Chapter 2. The Basics, Variables, Data Types, and Simple Operations Narrator. Now that we know why we're using Python, let's start casting some basic spells. In programming, the most fundamental concepts are variables and data types. If we continue our wizard analogy, think of a variable as a magic chest or container where you can store a value, like a piece of data, and give it a name for later use. You can put something into the chest, give the chest a label, and later refer to that label to get the item back out. For example, in Python code, spoken aloud, we write x=5 inches. This means, take the number 5 and store it in a container called x. If later we write print x, Python will fetch what's in x and show it, which would be 5. In an audio sense, you can imagine I have a box named x, and I say, x=5. The computer remembers that. Variables can change, too. That's why they're called variables. If I later say, x=7, the old value is replaced. It's like renaming what's inside the chest or swapping its contents. Every piece of data in Python has a type. Data type is the kind of thing a value is. Some basic types in Python include integer, a whole number, like 5 or -3, float, a number with a decimal point, like 3.14, string, text, like hello world, and Boolean, true or false values. Think of data types as the color of an item in our chest analogy. Red potion, blue potion, yellow potion. Each color might represent a type of magic. In your RBY theory terms, perhaps red can symbolize numbers, blue text, and yellow booleans. Just as a fanciful mnemonic, not scientific, but fun. When we combine these, we can create new effects, just as mixing primary colors yields new shades. Let's do a quick example in words. We set name equals Alice, a string type holding text. We set age equals 30, an integer type holding a number. We set is underscore student equals true, a Boolean type indicating a true, false condition. Now we can use these in sentences or operations. For instance, Python allows string concatenation, which is a fancy term for sticking strings together. If we do greeting equals hello, plus name. The variable greeting will now contain, "Hello, Alice." We used the plus operator on strings to join them. We can also do math with numbers easily. Python supports the basic arithmetic operations you'd expect: addition, plus, subtraction, multiplication, asterisk, division. If x equals 5 and y equals 2, then x plus y gives 7, x, y gives 3, x asterisk y gives 10, and x, y gives 2.5. Python respects the usual order of operations: parentheses, multiplication, division, then addition, subtraction. You can also use parentheses to make it explicit or change precedence, just like in normal arithmetic. One important thing for audio learning: in Python syntax, you often need to be precise about characters. For example, strings are enclosed in quotes, either single or double quotes. So when I said name equals Alice, those quotation marks are part of the code to denote a string. You won't see them in audio, but keep in mind that whenever I say a value is text, in code it would be wrapped in quotes. If I say a value is a number, it appears as is, no quotes, in code. Engaging analogy. Consider a toolbox. Variables are like labeled drawers where you keep tools, data. One drawer might hold a hammer, an integer, another holds sandpaper, a string of text description, another a switch, a Boolean true, false. You label them so you know which is which. Using them in code is like pulling tools out as needed to build something. Python's simple syntax is the friendly workshop guide, ensuring you pick the right tool for the right job. In terms of your conceptual frameworks, you might appreciate that even at this basic level, there's a unity. One might whimsically say, A equals C equals 1, in how data and labels interact. Whatever data, existence, you have, by giving it a name, you imbue it with meaning in your code, consciousness of that data, and it becomes a singular entity you can work with. That's a playful way to connect the idea, showing that with just a name and a value, you've created a single point of reference in the program's universe. No external sources needed for fundamental concepts here. These are general programming basics. Chapter 3. Control flow. Directing the path of logic narrator. Programs would be dull if they only ran straight from top to bottom without making decisions or repeating actions. This is where control flow comes in. The ability of your code to make choices and to loop, repeat tasks. In storytelling terms, this is where your program can say, if this, then do that. Otherwise, do something else, or do this thing 5 times, or even, keep doing this until some condition is met. 3.1 If-else. Decisions. The if statement is how Python makes decisions. It's like a fork in the road. If a condition is true, go one way. If not, maybe go another way. For example, in code speak, if temperature greater than 30, print, it's hot outside. Else, print, it's not too hot today. In plain English, that means, if the temperature is greater than 30, say, it's hot outside. Otherwise, say, it's not too hot today. Notice an important Python feature here. Indentation. The spaces before print, it's hot outside, in the code. In Python, indentation is not just for readability, it defines blocks of code. The fact that print, it's hot outside, is indented under the if means it's part of the if clause, i.e., it will only run if the condition is true. The line under else is similarly indented to align with the block under if. These indents, commonly 4 spaces, are how Python knows which lines belong to which part of the control structure. This is different from some other languages that might use curly braces to group code. In Python, whitespace is significant. It forces your code to be neatly structured, which actually helps readability a lot, one of the reasons Python is praised for clean syntax. Think of an if-else like a traffic signal for the flow of your program. Green light in one direction if a condition is met, otherwise green light in the other direction. If else chains, yes, there's also elif for else if, to check multiple conditions in sequence, or like a multi-way intersection with several possible turns, each labeled with a condition. 3.2 Loops. Round and round we go. Next up, loops. Loops allow your program to repeat a block of code multiple times. Python primarily offers two kinds of loops: for loops and while loops. A for loop iterates over a sequence, like a list of items, and runs the block for each item. It's like saying, for each element in this collection, do the following. For example, if you had a list of colors equals red, blue, yellow, a loop It's a straightforward way to handle repetition when you know the set of items or the range of numbers you need to go through. A while loop repeats as long as a condition remains true. It's like saying, while this condition holds, keep doing this. For example, count equals 1 while count less than equals 5. Print, counting. Count equals count plus 1. This will print counting. 1, then 2, 3, 4, 5 and then stop, because when count becomes 6 the condition count less than equals 5 is no longer true. A while loop is useful when you don't know exactly how many times you'll loop ahead of time, but you have a condition that eventually will end the loop. One must be careful. If the condition never becomes false, a while loop can run forever, an infinite loop. That's like a song that never ends, not usually what you want, so you design your loops to eventually break out. Now, let's bring in recursive singularity logic as a whimsical analogy here. We can think of a loop as a kind of recursion, though technically recursion in programming usually refers to functions calling themselves, which we'll touch on soon. But conceptually, a loop is a bit like a recursive process. It repeats and feeds back into itself. If you imagine each iteration of the loop as a step closer to some goal, it's like approaching a singularity. Each cycle brings you nearer, but you have to be careful or you get stuck orbiting forever. In AI, there's even a notion of a system that improves itself in a loop, a recursive self-improvement, which echoes the idea of a singularity. In our down-to-earth code, though, it's much simpler. You loop until you're done, then move on. Engaging analogy. Think of control flow as a choose-your-own-adventure book for your program. At decision points, if, elif, else, the program flips to different pages based on conditions. If you have a key, go to page 10, else go to page 20 inches. Loops are like finding yourself in a time loop in the story, repeating the same scene until you solve a puzzle. For example, while you haven't found the treasure, keep searching the room. Each loop is a repeat of actions, hopefully edging closer to the treasure, the loop's end condition. This storytelling perspective makes it easier to follow why and how a program changes course or repeats actions. As you craft code, you're essentially writing these branching stories and loops in logic. Python's syntax, with indented blocks under if or inside a loop, makes the structure apparent. When read aloud, you'll hear me emphasize structure like, if this, then do that, indent. Otherwise do something else. These are the inflection points where the program's path splits or repeats. No external citation needed for basic control flow, but remember, Python enforces structure through indentation, Making code blocks clear, a design decision that helps readability. Chapter 4. Functions. Packaging reusable logic narrator. As we write more code, you'll notice patterns or tasks that repeat. In programming, a key principle is don't repeat yourself. If you find yourself writing similar code more than once, it's often a sign you should wrap that code into a function. A function is like a named subroutine, a little machine that performs a specific task, which you can run, or call, whenever you need that task done. Imagine you are in a chocolate factory, channeling a bit of recursive singularity logic fun here, like a self-contained mini-factory within a factory. If you have to wrap a chocolate every time manually, that's tedious. Instead, you could have a wrapping machine that you activate whenever a chocolate needs wrapping. In coding, that machine is a function. In Python, we define a function using the def keyword. For example, def greet, name, message equals hello, plus name return message. This defines a function named greet that takes one parameter name. Inside, it creates a message by concatenating hello with whatever name was passed, and then it returns that message. The return statement hands back a result to wherever the function was called. Now, if elsewhere in our code we want to greet someone, we don't need to rewrite that concatenation logic. We can just do text equals greet, Alice, and our greet function will run, with Alice filling in for the name parameter, and we'll get back hello, Alice, in the variable text. We could call greet, Bob, and get hello, Bob, etc. We wrote the logic once, but we can reuse it for any name. Key things about functions. They can take input parameters, also called arguments when you call the function, like name in our example. You can have multiple parameters or none at all. They can produce an output using return. A function can return any type of data, or even multiple values in Python, by returning a tuple of values. They have their own little scope, meaning variables inside a function, like message above, are local to that function and don't interfere with variables elsewhere in your code. They help organize code logically. You might have one function to calculate the area of a circle, another to format a string, another to filter a list of data, etc. Each function does one thing well. This aligns with another programming mantra. Each function should ideally do one thing and do it well. Using functions makes programs modular. This modular design is crucial as projects grow. It's like building with Lego blocks. Each function is a block that can be developed, tested, and reasoned about independently, and then combined to form a larger system. In fact, code modularity and clarity are often cited as signs of high-quality code. Code that is easy to understand, maintain, and reuse. Think of functions as skills or techniques you master. If your program is a story, functions are like chapters or even little side quests that can be reused in the tale. They make the narrative, flow of the program, cleaner by abstracting details. Instead of describing in detail how to do a task every time, you just invoke the function. The reader of code can assume it does its job and not worry about the inner mechanics each time. Engaging analogy. Imagine you're directing a play. Your code is the play. Functions are like the choreographed routines or scenes you can call on demand. Scene 1. Greet the audience. Lights on. Actor says hello. That's our greet function. Scene 2. Perform a dance. Cue the dance routine, another function for dancing. If you need the dance again later, you don't re-choreograph it. You just call that scene again. This reusability is powerful. In our Python audio journey, I might not read out long function definitions, but I'll describe what they do and why they help. It's like hearing about a gadget in a story. You don't need the blueprint, just what it accomplishes. And indeed, under the hood, functions are our gadgets that encapsulate code for repeated use. Supporting idea. Modular design and clear structure with functions are part of Python best practices. Keeping code flat, rather than overly nested, improves readability, which functions can help with by avoiding deeply nested logic. Chapter 5. Modules and imports. Structuring larger codebases. Narrator. As your programs become more ambitious, you'll soon have dozens of functions and perhaps a lot of variables and logic. Putting everything in one file becomes unwieldy. It's like writing a novel as one gigantic chapter. To manage complexity, Python allows you to spread your code across multiple files and organize it into modules and packages. This is how you structure a codebase for clarity and maintainability. A module in Python is simply a file containing Python code, usually with a py extension. Each file can define functions, classes, we'll get to classes soon, and variables. When you want to use those in another file, you use the import statement. Importing is like saying, bring in this other file so I can use its goodies. For example, suppose you have a file math_utils.py where you define a function square x that returns x** x and another function cube x that returns x** xx. In your main program file, you could write import math_utils. Now you have access to those functions via the module name. You could call math_utils square 5 and get 25. If you have many functions, grouping them logically into modules, files, helps keep things organized. Maybe math_utils.py for math functions, string_utils.py for text-related functions, etc. There's also another form. From math_utils import square. This line would import only the square function directly, so you can call square 5 without the module prefix. However, a common best practice is to import the whole module or specific names explicitly rather than using the from module import import everything form. Why? Because it keeps it clear which names come from where. Explicit is better than implicit in Python culture. If you see math_utils square, you immediately know square is defined in math_utils. This clarity prevents the kind of confusion where two modules have functions of the same name and one might overwrite the other in the namespace unknowingly. If your project grows even larger, modules can be grouped into packages, which are basically directories containing multiple module files, often with an __ in it __.py file to indicate to Python that the directory is a package. You might have a package my package with modules inside it like my package/data_processing.py and my package/model_training.py, etc. And you can do from my package import data_processing to get that module. The details of Python's import system can get intricate, but at a high level, it's designed to enforce structure. By splitting code into modules and packages, you enforce logical separation of concerns. Each module handles a specific aspect of the project. This is crucial in large AI systems. For instance, you might separate code that handles data ingestion from code that defines the neural network model, and separate that from code that handles evaluation metrics. This way, each part can be developed and tested in isolation. It mirrors how large engineering projects are broken into sub-components. Engaging analogy. Think of modules like chapters in a book, and packages like sections comprising multiple chapters. If someone is reading, or listening, to your code story, Modules let them jump to the chapter of interest instead of wading through one enormous script. Another analogy. In a workshop, modules are like separate toolboxes for different tasks. One toolbox has carpentry tools, another has electrical tools. You bring out the specific toolbox, module, when you need those tools. This organization prevents mixing everything into one big chaotic pile. Let's connect to your frameworks creatively. Using RBY theory, imagine each primary color as a different aspect of your project. Say red equals data handling, blue equals model training, yellow equals deployment. You wouldn't store red paint in the blue paint can. You keep them in separate containers and mix as needed. Modules are those containers. They keep things clean and separate until you intentionally mix them via imports to create the complete picture, your AI application. A quick note on traceability. When your project has good structure, it's easier to trace errors or update code. For example, if something goes wrong with data loading, you know to look in the data module. This segmentation is not just about aesthetics, it's about managing complexity. Big AI systems can have thousands of lines of code, and without modules, it'd be almost impossible to navigate. As the Hitchhiker's Guide to Python notes, structure, modules, imports, project layout, is a central element for maintainable code. It ensures logic and dependencies are clear and that files and folders are organized logically. A well-structured project makes a good first impression and is easier for collaborators and your future self to understand. Cite. It's important to leverage Python's module and import system to enforce structure in your project. Keeping code organized into modules, with clear, flat imports, makes it more readable and avoids confusion. Chapter 6. Diving into object-oriented waters. Classes and OOP narrator. So far, we've dealt with functions for behavior and used basic variables and data structures, like lists or dicts, which we mentioned in passing, for data. Now it's time to talk about classes and object-oriented programming, OOP. A paradigm that Python supports, alongside the simple function-based approach, for structuring code, especially when modeling complex systems. A class is like a blueprint or template for creating objects. If functions are like verbs, actions your code can take, classes are like nouns. They define concepts or things that have both attributes, data, and methods, functions that operate on that data. If this sounds abstract, think of a class as a cookie cutter and objects as the cookies. Or think of a class as a blueprint for a house, and each object as a house built from that blueprint. The blueprint defines that every house will have certain properties, number of rooms, square footage, and behaviors. Doors can open, lights can turn on. For example, imagine we're building a simple game. We might have a class player, def ___ init ___, self, name, level, self.name equals name self, level equals level self, health equals 100 def take _ damage, self, amount, self, health equals amount. What's happening here? We defined a class player. Inside it, we have a special method __init __, which is the initializer, often called a constructor in other languages. This method runs when we create a new player object, and it sets up initial attributes. Here it takes name and level as parameters, and sets self.name, self, level, and also initializes self, health to 100. Self refers to the instance of the class, the specific object being created or used. We also have a method take _ damage which reduces the player's health by a given amount. It's a behavior associated with the player. Using this class, we can create objects, instances, player 1 equals player, Alice. 5. Create a player named Alice at level 5. Player 2 equals player Bob. 3. Create another player named Bob at level 3. Print player 1. Name outputs Alice. Player 2. Take underscore damage 20. Print player 2. Health outputs 80. Since Bob's health went from 100 to 80, each object player 1 and player 2 has its own independent data, name, level, health. They both follow the same structure defined by the class, but they maintain their own state. This is powerful for modeling real-world or conceptual entities in code. In AI development, you might use classes to represent, say, a neural network class or a dataset class, encapsulating properties and behaviors related to each. For example, a neural network class might have methods like train, data, and predict, input, and attributes like layers or learning underscore rate. Organizing code with classes can make it clear how different parts of the system relate to each other. It's a way to bundle data and functionality together. However, it's worth noting that Python is multi-paradigm. You can do a lot in a simple script with functions and not a single class. But as designs grow, OOP can help manage complexity by grouping related code. Engaging analogy. Think of classes as characters in a story. Each class, character type, defines what attributes the character has. Warrior characters have strength, agility. Mage characters have mana, intelligence, and what actions they can perform. Warriors can attack, defend. Mages can cast spells. When you create an object, it's like creating a character in the story with specific values for those attributes. Alice is a warrior with strength 10. Bob is a mage with mana 50, etc. The methods are like the character's abilities. This narrative way of thinking can make it intuitive. You design a class like you flesh out a character profile, and then your program can create many characters from that one template. In terms of your conceptual frameworks, if we talk about A equals C equals 1 as a oneness of existence and consciousness, one could whimsically say classes bring together data, state, existence of attributes, and behavior, methods, actions which could be likened to a form of consciousness or decision-making, into one entity, the object. It's a stretch, but it's a poetic parallel. The object is a single unit that knows how to act on its data. In practice, to keep our audio journey light, we won't dive too deep into OOP intricacies like inheritance or polymorphism, where classes can inherit traits from other classes, etc. But know that Python classes support those too, allowing very sophisticated designs. For now, think of classes as another organizational tool. If some data and functions naturally belong together, a class lets you encapsulate them neatly. General knowledge reference. Classes are a way to structure code by bundling data and functions. They improve modularity and reusability, aligning with principles of clean code. We'll treat this conceptually. No specific external citation needed for the basic explanation. Chapter 7. Errors and Exceptions. Learning from Traceback's narrator. Let's shift gear to something every programmer encounters. Errors. As a beginner, and even as an expert, you will inevitably write code that has bugs or unexpected conditions. When something goes wrong during program execution, Python will typically throw an exception and display a traceback. The first time you see a Python error message, the traceback, it can look intimidating, a multi-line dump of information. But it's actually a very useful guide that tells you what happened and where. First, what's an exception? It's Python's way of saying, I can't continue because something unexpected, harmful happened. For example, if you try to divide by 0 in Python, 10 * 1 over 0. As a simple case, Python will raise a zero division error exception. If you try to access a variable that hasn't been defined, you'll get a name error. If you try to add a number and a string, 2 plus 2, you'll get a type error because Python doesn't know how to add those two mismatched types. These exceptions are not unconditionally fatal, meaning your program doesn't have to crash if you're prepared to handle them. You can catch exceptions and do something about them, which we'll cover shortly. The traceback is the report Python gives when an exception isn't handled and is about to crash the program. It includes the sequence of function calls that led to the error, effectively the path the program took through your code, and ends with the line telling you what the error was. If you read a traceback from the bottom up, you usually find the actual error type and message at the very bottom line, and above it the lines of code, with file names and line numbers, that were executed leading to that point. This is incredibly useful for debugging. It's like a breadcrumb trail left by the program as it ran, showing exactly where things went wrong. For example, if you see at the bottom, name error, name, someone, is not defined, and above it, it mentions which line in your code raised that, you can deduce you probably misspelled a variable name. Maybe you meant someone but wrote someone. The traceback has pointed out the offending line and error cause. In an audio context, I might narrate an error like, traceback, most recent call last, file less than stdin greater than, line 1, in less than module greater than. Name error. Name, someone, is not defined. While hearing it isn't as immediately clear as seeing it formatted, the main point is the error message at the end. Name, someone, is not defined. That tells you the problem. So, how do we handle exceptions? Python provides the try, except construct. It works like this. Try. Hash code that might raise an exception x equals int. Input. Please enter a number. Print. You entered. X. Except value error. Print. Oops. That was not a valid number. In this snippet, Python will attempt to execute the code in the try block. If no exception occurs, the except block is skipped entirely. If a value error occurs, for instance, if the user inputs something that int cannot convert to a number, Python raises a value error. Then the rest of the try block is skipped and the program jumps to the except value error block, executing the print there. After that, the program continues after the whole try, except structure. You can have multiple except clauses to handle different types of exceptions differently, and even a generic except exception to catch any exception. Though catching too broadly can sometimes hide bugs you didn't anticipate, so usually we catch specific errors we know might happen. The idea is, by handling exceptions, your program can fail gracefully or recover, instead of just crashing outright. For example, in an AI data ingestion script, you might catch network exceptions if a data source is unavailable and retry, rather than the program just dying on first failure. Or in a user interface, if something goes wrong, you might show an error message to the user instead of just exiting. One more aspect: cleanup actions. Often you want to ensure some cleanup happens regardless of success or error, like closing a file or releasing a resource. Python provides finally blocks or context managers, with statements, for that, but those details might be too fine-grained for now. Just know that the try, except can also have a finally clause which executes no matter what after either the try succeeded or an except ran. Engaging analogy. Think of exceptions like roadblocks on your journey. The traceback is the map that shows you where the roadblock happened. If you're driving, running your program, and suddenly there's a roadblock, exception, you stop. But if you have a plan, try, except, it's like having a detour route ready. You encounter the obstacle but then take the alternate path. the accept block, and continue driving after the detour. Another creative angle. In your conceptual realm, maybe recursive singularity logic implies learning from each iteration or loop. Similarly, each exception can be a learning point. It tells you something about a case you didn't handle. Over time, handling exceptions is like making your code more resilient and intelligent, almost as if the program learns what to do when something unexpected happens, though it's you, the programmer, doing the learning and then coding the handling. In summary, don't fear errors. The traceback is your friend. Read it, understand it. It often literally tells you what went wrong, like file not found or index out of range. Use that info to fix the issue or handle it. Many great programmers often say that knowing how to debug, that is, read tracebacks, print out values to narrow down issues, etc., is half the skill of programming. And Python's errors are quite human-readable compared to many languages, once you get the hang of their format. Embrace them as part of the process. Cite: Python exceptions are not unconditionally fatal and can be handled. A traceback is essentially a report of function calls leading to the exception, useful for diagnosing issues. Reading from bottom up, the last line states the error type and message. Chapter 8. From Scripts to Pipelines. Real-world AI development flow narrator. We've built up from the ground. Variables, functions, classes, error handling. Now it's time to zoom out and see how Python is used in the context of building AI systems, specifically, the workflow or pipeline of developing an AI model or application. When we say AI development pipeline, what do we mean? In practical terms, it's the series of steps or stages that take you from raw data to a working AI model in production. Typically, an AI, or machine learning, pipeline includes steps like 1. Data ingestion, getting the data from various sources. 2. Data processing, cleaning, filtering, transforming, and preparing data for modeling. 3. Feature engineering, extracting or creating meaningful variables, features, that might help the model. 4. Model training, using the processed data to train an AI, ML model. This is where the learning happens. 5. Model evaluation, checking how well the model performs on test data, ensuring it generalizes well. 6. Inference, deployment, using the model to make predictions on new data, inference, and deploying the model into a real-world system or product. 7. Monitoring, once deployed, monitoring the model's performance over time, catching data drift or performance issues, and possibly looping back to update the model. This might sound abstract, so let's ground it with a simple real-world scenario. Suppose we want to build an AI system that predicts whether incoming emails are spam or not spam. The pipeline would be: data ingestion, collect a dataset of emails with labels spam, ham, not spam. Data processing, clean the text, remove HTML tags, lowercase everything, maybe remove stop words. Feature engineering, perhaps convert emails into numerical features, like word counts or embeddings. Model training, split data into training and testing sets. Train a machine learning model on the training data to classify spam versus not spam. Model evaluation, test the model on the reserved test set, see accuracy, precision, recall, etc. If performance is good, proceed. If not, maybe tweak features or model and retrain. This loop can happen many times. This is the iterative part of model development. Inference, deployment. Integrate the model into an email server so that as new emails come in, they get scored by the model, and suspicious ones are filtered out. This might involve writing a Python service or script that loads the trained model and applies it to each new email. Monitoring. Keep an eye on how the model is doing on live data. Maybe log some stats and retrain with fresh data if needed after some time, which takes you back to step 1, making it a continuous pipeline. In professional environments, these pipelines are often automated and orchestrated with tools. Python is commonly used to script these steps and glue them together. For example, using libraries and frameworks. Data ingestion might involve Python code to read from databases or APIs. Data processing could use libraries like Pandas for data frames or NumPy for numerical processing. Feature engineering might use domain-specific libraries or custom Python code. Model training likely uses frameworks like scikit-learn, TensorFlow, or PyTorch, all of which are Python-based or have Python interfaces. Evaluation could use libraries for metrics. Scikit-learn has a lot of metrics functions, for instance. Deployment might use web frameworks, Flask, FastAPI in Python, to create an API for the model, or job schedulers if it's batch inference. Monitoring might integrate with logging libraries or external monitoring systems, but Python can still be involved. For instance, a cron job in Python that checks model quality periodically. Let's map this to a generic AI pipeline structure. AI pipelines cover everything before and after model training, gathering data, processing it, and taking action on model outputs. Meanwhile, a narrower ML pipeline focuses just on the model's train test deploy cycle. You can imagine an AI pipeline as the full story, whereas the model training is one chapter in that story. From another perspective, an AI pipeline ensures that repeatability, scalability, and efficiency are baked into the process. Repeatability means if you feed the same input, you reliably get the same process and output, great for consistency. Scalability means you can ramp up from handling 10 data items to 10,000 without breaking the design, crucial when your AI project grows. Efficiency means you minimize wasted time or manual effort. The pipeline automates tasks so you or your team aren't doing things by hand each time. A concrete example. Consider an AI pipeline at a company like a spam filter for millions of users. It might ingest new emails in real time, use a trained model to classify, move spam emails to a spam folder. That's an action based on model output, and perhaps periodically retrain the model on newly collected data to adapt to new spam techniques. All these steps can be orchestrated. Modern systems might use tools like Airflow or other workflow managers to schedule and connect steps, but at the code level, it's often Python making the calls, like a Python script that triggers training, etc. We can also talk about data pipelines versus model pipelines. A data pipeline deals with getting data from sources, through maybe an ETL, extract, transform, load, process, into a state ready for ML. The model pipeline picks it up to train and then deploy models. Python, being versatile, is used in both contexts. Now, one interesting concept. Sometimes AI development involves multiple environments or machines, like a big data cluster or special hardware like GPUs. Python is still often the coordinator. For example, you might use Python to send a training job to a remote server or cluster. This is where it starts overlapping with HPC, high-performance computing, which we'll get into next. But before that, let's tie in a bit of your creative framework flair. One could compare an AI pipeline to recursive singularity logic in a loose sense. After deployment, you often loop back with new data to improve the model, creating a feedback loop. It's like the pipeline is recursive, output, deployed model, comes back later as input, retraining with new data. If unchecked, Maybe one imagines a singularity where the AI keeps improving itself, but in reality, it's guided by us. This is a creative way to see the pipeline as a learning loop. Also, reminiscent of RBY theory, think of three primary phases like data, input, the raw info, model, the logic that transforms data, and decisions, output action. Combining them yields a functioning AI system, just like combining primary colors yields a full picture. It's a stretch, but it gives a narrative. First gather raw ingredients, red, then apply intelligence, blue, then achieve results, actions, yellow. Engaging analogy. If coding is storytelling, an AI pipeline is like a whole book series. Each book is a phase. First book where you gather characters and setting, data. Second where a hero trains, model training. Third where the hero is tested, evaluation. And further volumes where the hero is deployed into the world and we see consequences, deployment and monitoring. And sometimes you loop back to an earlier volume for a prequel or a retraining sequel. Python is the author writing the story, ensuring continuity and coherence across volumes. In practical terms, building an AI pipeline with Python might involve writing multiple scripts or using a framework. One script to fetch or pre-process data. One notebook or script to experiment with models and training. Another to evaluate and maybe save the best model, serialization, e.g., saving a model as a file. Then integrating that model into an application, maybe a microservice in Flask that loads the model and responds to queries. And then maybe a monitoring script or just logging within the application. There are specialized tools, like ZenML or Kubeflow pipelines, that help define pipelines, where you write Python functions for each step and the tool helps chain them. For example, ZenML uses Python decorators to mark pipeline steps and handles orchestrating data flow between them, making it clear and maintainable. Underneath, it's all Python logic organizing tasks such as data ingestion, pre-processing, model training, and evaluation into a coherent flow. By understanding the idea of a pipeline, you get the concept of how an AI project moves from raw data to deployed model. This big picture can guide how you structure code. Each of those steps could be one or more modules in your codebase. And you might even have separate Python environments or configurations for different steps. For instance, training might run on a GPU machine with certain libraries, whereas deployment might be a lightweight environment with just inference code. Cite. An AI pipeline encompasses everything from data ingestion to using model outputs in action. It typically includes data collection, preparation, model training, tuning, evaluation, and deployment. Organizing these into a structured workflow ensures repeatability, scalability, and efficiency. Chapter 9. Scaling up with high-performance computing. HPC. Narrator. As your projects grow, you might run into limitations on a single machine. Maybe training your AI model on your laptop takes 2 weeks, or the data is too large to fit in memory. This is where high-performance computing, HPC, and distributed computing come into play. HPC often refers to using clusters of powerful machines, or a supercomputer, to perform large computations in parallel. You mentioned AIOSIO Global HPC, which I gather is a conceptual high-performance platform in your context. Even if it's conceptual, let's talk about how Python fits into HPC scenarios generally, so you can imagine integrating your Python programs into such a platform. On a typical HPC cluster, you have many nodes, computers, networked together. Instead of running a program by double-clicking it, you often submit a job to a scheduler, software like Slurm, PBS, or others. The scheduler finds resources on the cluster to run your job, like assigning it to a node with X CPUs or a GPU for Y hours. HPC is all about handling big tasks by using a lot of resources concurrently and efficiently. How do you integrate Python here? There are a few levels. Batch jobs. You can write a normal Python script to do your task, say train a model on a big dataset. Then you write a job script, a shell script with directives for the scheduler, e.g., slurm. That essentially says, run this Python script using these resources. For example, in Slurm you might have a job script with lines like #SBATCH CPUs per task equals 8 to request 8 CPU cores. And then at the end Python my_training_script.py. When you submit this job, e.g., via sbatch for Slurm, the cluster will eventually execute your Python script on a compute node with the resources you asked for. Python itself doesn't change. It's the same code, but you leverage the cluster to run maybe faster, if you use multiple cores, or just to not tie up your own machine. Parallel, distributed computing. If one machine isn't enough, you might use libraries that allow Python code to run in parallel across multiple nodes. For example, MPI4PY, MPI for Python, can coordinate multiple Python processes across nodes in an HPC cluster. Or frameworks like Dask can distribute data and computation in Python. For machine learning specifically, libraries like PyTorch or TensorFlow can scale to multiple GPUs or even multiple nodes, using built-in distributed training utilities. HPC specifics. On many HPC systems, you might need to module load certain versions of Python or libraries. Clusters often have modules for different software. In an example from USC's HPC guide, they stress not to run heavy Python jobs on the login node but to allocate a compute node via the scheduler and then run Python. They even show interactive use, using Salak to get a node, then launching Python interactively. This is more for interactive exploration. For batch, they demonstrate writing a Slurm script with the Python script.py command in it. In your conceptual AIOSIO Global HPC, I imagine it's a platform where Python programs can be deployed to a global high-performance infrastructure. So think of it like writing your Python code on your local machine, then sending it to the cloud or cluster where it runs on maybe dozens of machines or high-end servers. You might have to adapt parts of your code to be HPC friendly, for instance, ensure it can run in parallel, or doesn't do things that only work on one machine. But Python is widely used in HPC for tasks like orchestrating workflows or even writing the core compute. Though for heavy number crunching, often underlying libraries in C, C++ are used, but they are invoked through Python. One practical pattern is to use Python as the glue and use optimized libraries for the heavy bits. For example, a Python script might call out to parallelized C code or use NumPy, which under the hood uses efficient C, so that even on HPC it's efficient. But if pure Python loops had to run across thousands of cores, that could be slow. Often you would vectorize operations or use libraries that know how to utilize multiple cores. Like NumPy can release the GIL and use multi-threading in some operations, or use multi-processing module to run separate Python processes on different cores. However, there's also the scenario of using HPC for automation. Python can be used to submit multiple jobs, gather results, etc. For example, you might write a Python script that launches 100 training jobs with different parameters on an HPC cluster. This falls under hyperparameter tuning, common in AI, where you try many combinations in parallel, a perfect use for HPC. There are Python libraries, like cluster job or workflow managers, that abstract the submission of jobs to HPC schedulers. The key integration point: imports and environment. On HPC, you often have to ensure your Python environment has the needed libraries. This might mean installing packages in your user space or using provided modules. Tools like Conda can help create environments that you can replicate on the cluster. Sometimes containerization, like using Docker or Singularity images with Python and libraries, is done to ensure consistency across HPC nodes. From the narrative perspective, HPC is like calling in the cavalry for your code. If normal Python programming is a lone warrior, HPC is an army of CPUs, GPUs. You, the commander, via Python scripts, tell the army what strategy to execute. Integrating your code with HPC is learning how to give those orders, job scripts, parallel code, and how to gather the results back. Engaging analogy. Visualize a scenario. You have a gigantic tome of calculations to do, like training a huge AI model. With a single computer, it's like one scribe copying a book. It could take ages. HPC is like having a scribe's scriptorium, hundreds of scribes, workers, who you can assign to copy pieces of the book simultaneously. But you, as the master scribe, the Python script, need to coordinate, maybe split the work, give each scribe a part of the text, data partitioning, and then compile the finished pages together, aggregating results. The job scheduler is like the chief librarian who assigns desks to your scribes and ensures they have ink and parchment, the resources. You fill out a request. I need 100 scribes for 2 hours. The librarian checks the hall, finds space, and then says, "Granted, you'll work at tables 5 to 10. Then your Python instructions are given to each scribe. In practical terms, how might you incorporate HPC in code? For AI training, many frameworks handle multi-GPU or multi-node training if launched appropriately, often via command line or small code tweaks. For simpler custom code, you might use Python's multiprocessing to utilize multiple cores on one node, or MPI to spread across nodes. One thing to note: HPC might force you to structure your program differently. For example, if using MPI, you often write one Python script that runs in n processes and you differentiate by process rank, so each process does part of the work. If you use a cluster but just run one process that internally is multi-threaded, that's simpler from coding perspective. Just ensure you utilize threads or vectorized ops. Your mention of AIOSIO Global HPC suggests maybe an interest in an AI operating system on a global HPC network. If we imagine that, Python code might be one component that such a system can run. Perhaps the HPC platform has an interface where you submit Python code, or notebooks, and it parallelizes them. For instance, services like Google Colab or cloud providers allow running notebooks on more powerful instances, which is conceptually similar. Though not exactly HPC clusters with job schedulers, but it's about offloading to big compute. To tie it to earlier topics, HPC might come into play at the pipeline stage of model training, because training can be HPC intensive, especially for deep learning on big datasets, or at the stage of data processing if the data is huge. So the pipeline might branch out to HPC for certain steps, then back to a local environment for others. Using Python throughout ensures compatibility. The same language orchestrates it end to end. Cite. Running Python on an HPC often involves writing a job script that loads the necessary modules and executes the Python program with the requested resources. For example, on a Slurm-based cluster, you'd create a job script with resource directives and a line like python script.py to run your program. This allows leveraging the cluster's nodes to execute your Python code in parallel or on beefier hardware. Chapter 10. Python and LLMs. Partnering with AI to write AI narrator. One of the exciting frontiers in programming and AI is using large language models, LLMs, like OpenAI's GPT series or others, as assistants or even as part of your application. You've expressed interest in using Python to develop and integrate LLMs, including prompting them to generate code, checking that code, and then executing or deploying it. This is like having an AI pair programmer or copilot who can suggest code, while you, or your program, verify and utilize it. Let's break down what this means. Prompting LLMs to generate code. With Python, you can interface with LLM APIs. For example, using the OpenAI API, Hugging Face API, etc. You send a text prompt that asks the model for code. For instance, your Python program might send a prompt. Write a Python function that takes a list of numbers and returns the sorted list. The LLM would respond with a code snippet. Checking for errors. The code the LLM produces might not be perfect. It could have mistakes, maybe syntax errors, maybe logical errors, maybe it uses a library you don't have, etc. A robust pipeline will then attempt to run the code, possibly in a sandbox or controlled environment, and catch exceptions or failures. If an error occurs, you can capture the error message, the traceback. Feedback loop. You can then feed that error message back into the LLM with another prompt like, "The code you provided raised this error. Error message. Please fix the code." In doing so, you're making the LLM iteratively refine its output. This idea of an AI debug loop is actually an area of active experimentation, building systems that keep prompting the LLM to correct itself until the code runs successfully. Executing or deploying outputs. Once the LLM gives a code that passes your tests or at least runs without exceptions, your Python program can then use that code. This could mean directly executing it, e.g., via Python's exec function, or writing it to a py file and importing it, or packaging it into a microservice, etc. Deployment could mean using that code as part of a larger system, perhaps automatically if it's generated correctly. Why do this? Well, one scenario is accelerating development. The LLM writes boilerplate or even complex sections of code, and you integrate it quickly. Another scenario is using LLMs to adapt code on the fly. Imagine an AI system that can rewrite parts of itself based on new requirements. That's very meta and experimental, but theoretically possible. However, we must consider the reliability of LLM-generated code. LLMs, as of 2025, can produce impressively correct code in many cases, but they can also produce subtle bugs or outright errors. They rarely make simple syntax mistakes. They're good at correct syntax, but logical correctness is not guaranteed. The model might fulfill the prompt in a superficial way but not actually solve the underlying problem correctly. That's why the step of checking and testing the code is crucial. The good news: if there are clear errors, like using an undefined variable or calling a non-existent function, those manifest as runtime errors or exceptions, which, as we know, produce tracebacks. As one AI commentator joked, hallucinations in code are the least dangerous form of LLM mistakes, because the moment you run the code, any made-up nonsense typically results in an error that you can catch. This is unlike, say, an LLM writing a plausible-sounding but factually wrong essay. There's no immediate crash to tell you it's wrong. With code, execution is a pretty good test. It either runs or it breaks, or produces incorrect output which you can detect via tests. So a Python program managing an LLM could do something like 1. Prompt LLM for code for a specific task. 2. Save the returned code to a file or in a string. 3. Try to run it, possibly with test inputs if you have an idea of what it's supposed to do, or at least to see if it runs without exceptions. 4. If there's an error, capture the traceback and send a new prompt to LLM. Your code produced this error, please fix it. This is akin to giving the AI feedback. Some research and projects use this idea of feedback-based generation, often calling it REACT or other agent loop strategies. 5. Repeat until code runs or a certain number of iterations is reached. 6. Once it works, possibly run a more thorough test to ensure it actually does what it's supposed to, logic-wise, not just syntax. 7. Then integrate that code by calling its functions or deploying it. There have been experimental systems, like AutoGPT or other AI agent frameworks, that attempt such loops, effectively letting an LLM iteratively refine outputs with a kind of memory or feedback. It touches on the idea of an AI improving itself, quite fascinating and also a bit reminiscent of a recursive singularity concept, though currently it's far from an autonomous singularity. It's more like a guided iterative improvement. Now, integrating LLMs into larger systems. Aside from code generation, you might use LLMs for tasks like summarizing data, generating text for reports, conversing with users, etc. In those cases, you also prompt from Python, get a response, and use it. The principle of checking is still important. You might validate that the summary meets some criteria or that the answer is in a certain format. A particularly relevant integration is using LLMs for things like code explanation or documentation. For instance, you could have Python scripts that generate documentation for code by asking an LLM to explain it, just an idea. Or use LLMs in test generation. Feed the code to LLM and ask for test cases, then run those tests. You essentially have an AI QA assistant. With great power comes great responsibility. One should be mindful of security when executing LLM-generated code. Because if the model is not aligned or the prompt is not careful, it could produce malicious code, like deleting files or something. If you're automating code execution, ideally run it in a sandbox or at least review it if possible. There's active research on ensuring the safety of LLM-generated code. Engaging analogy. Think of an LLM as a genie who writes code. You, the developer, speak to the genie in Python via API calls and say, "Build me this tool." The genie scribbles some code. Now, as any savvy wishmaker would, you test the genie's creation. Does the tool actually work? If it doesn't, you tell the genie, "This doesn't quite work because of X, please fix it." It's a bit like those fairy tales where a wish can go wrong if not phrased carefully, but here you have the chance to iteratively refine the wish. In your conceptual frame, this is a creative synergy between human and AI. The LLM, perhaps representing an aspect of C in your AE equals C equals 1, if we metaphorically say the I is injecting some consciousness into code, and you bring the execution to unity by iterative refinement. And recursively, the I improves the artifact it created, which is like a loop of creation and feedback. One might whimsically call it a recursive improvement loop, inching towards some ideal solution. Not quite a singularity, but an optimizing process. Another angle. LLMs in deployment can become part of the pipeline we discussed. For example, an AI pipeline might use an LLM at some stage, like to interpret a user's request in natural language before deciding which model to run, etc. Python is commonly used with LLMs thanks to frameworks like Hugging Face's Transformers library or OpenAI's Python API. So practically, you'd have code like import OpenAI openai.api_key equals hash your API key response equals OpenAI. Completion. Create model equals text DaVinci 003. Prompt equals write a Python function to check if a number is prime. Max_tokens equals 100. Code equals response, choices, 0, text. Then you might strip out any markdown or extra text the LLM gives, and attempt to run that code. It might produce a prime check function. If it forgot to handle a case or had a bug, you'd catch it and prompt again. Cite. LLMs can produce working code but often require validation. They rarely make syntax errors, but logical mistakes are common. Running the LLM-generated code and feeding back errors can help the LLM correct itself, creating a loop where the AI keeps fixing the code until it runs properly. Chapter 11. Best Practices. Writing Clean, Sustainable Code Narrator. As we near the end of our journey, let's talk about how to write code not just that works, but that stays working, can be understood by others, and your future self, and can scale up to larger projects. In other words, let's discuss best practices for project development in Python. Key themes to touch on: modular design, readability, version control, and scaling. We already hinted at some of these, but we'll consolidate them here with some actionable advice. 11.1 Modular design. We covered this when talking about functions, modules, and classes. Modular design means breaking your program into pieces, modules, functions, classes, that each have a clear responsibility. Aim for a low coupling, high cohesion approach. Within a module or function, everything should be closely related to a specific task. High cohesion, and different modules should depend on each other as little as reasonably possible. Low coupling. This way, changes in one area have minimal impact on others, and you can modify or replace one part without rewriting everything. In practice, use functions to avoid repetitive code. Organize functions into modules logically, e.g., a utils module for utility functions, a data module for data handling, etc. If some data and functions naturally form an entity, consider a class to encapsulate them. Keep each file at a manageable size. If one file grows too big, hundreds of lines doing many things, that's a smell that it could be split up. Modular design helps in collaborative settings too. Different team members can work on different modules simultaneously with fewer merge conflicts. 11.2 Readability. There's a famous guiding principle in Python. Readable code is more valuable than clever code. Pythonistas often follow the PEP 8 style guide, which is a document outlining conventions for Python code, like naming variables in snake_case, keeping line length around 79 characters, using spaces around operators, etc. Following a consistent style makes code easier to read. Tools like linters, Flake 8, Pylint, and auto-formatters, Black, can help enforce style automatically. Readability also involves naming things clearly. Use descriptive variable and function names. Compare f equals get_freq, x, versus word_frequencies equals get_word_frequencies, text. The second is longer, but when you read it, you immediately understand what it likely does. According to best practices, good code uses descriptive names for variables, functions, classes, etc., to make the code self-documenting. Document your code. Write comments to explain non-obvious things, or doc strings for functions, classes to describe their purpose and usage. However, Don't overcomment obvious things, like I equals I plus 1 hash add 1 to I is unnecessary. Comment why something is done if it's not clear, more than what the code is doing, since the code itself shows the what. Another aspect. Keep functions and classes focused, as mentioned. If a function is more than, say, 50 lines, consider if it can be broken into subfunctions. Long functions can often be split by logical subtasks. Remember the Zen of Python line: flat is better than nested. This means try not to have too many levels of nested loops or ifs, which can become hard to follow. Sometimes restructuring logic or breaking parts into functions can flatten complex logic. 11.3 Version control. If you're not already using it, learn to use version control systems, primarily Git, the most popular. Git allows you to track changes in your code over time, collaborate with others without stepping on each other's toes, and revert to earlier versions if something goes wrong. Platforms like GitHub or GitLab host repositories where you can push your code and even integrate things like issue tracking and continuous integration. For a beginner, the key things to learn in Git: how to make commits, snapshots of your code with a message; how to branch, create a separate line of development to try something or to develop a feature, then merge it back in; and how to push to, pull from a remote repository, like on GitHub. Using Git, you can experiment fearlessly. If a change doesn't work out, you can revert to a previous commit. It's like a time machine for your code. In the context of AI projects, version control also extends to data and models in a sense, though Git isn't used for large data files typically. Tools exist for dataset and model versioning, like DVC or MLflow, but that might be beyond scope here. Still, conceptually, you want to track which code, and hyperparameters, produced which model so experiments are reproducible. Good practice is to log parameters and random seeds, etc., when training models, and to save models with clear naming or versioning. 11.4 Testing. Though not explicitly requested, I'd be remiss not to mention testing as a best practice. Writing tests for your code, using frameworks like Unitest or PyTest, ensures that as you modify code, you can automatically verify that it still behaves as expected. This becomes important as codebases grow. For example, if you have a function that cleans data, you might write a test that feeds it known raw input and asserts that the output matches an expected cleaned version. Later, if someone changes the cleaning logic, the test will catch if they broke something. Testing is part of writing robust, scalable code. 11.5 Scaling and performance. When scaling an AI system, there are a couple of dimensions. Scaling the software design, which modular design, OOP principles, etc., help with, so that you can handle more features, more contributors, bigger codebase without losing control. Scaling performance to handle more data or higher load. This might involve moving to HPC or distributed systems, which we discussed, optimizing algorithms, using more efficient data structures or algorithms with better complexity, or using more efficient libraries, leveraging C-optimized libraries or writing critical parts in a faster language if needed. In Python, one performance tip is, use built-in data structures and libraries, like lists, dicts, pandas, numpy, etc., which are optimized, rather than writing very slow Python loops for heavy computations. Often, one can achieve huge speedups by moving work into numpy arrays, which do operations in C under the hood, or using list comprehensions and generators wisely. Also, consider the complexity, e.g., avoid deeply nested loops over large data which could be O(n squared, or worse, if an algorithm with O(n log n exists. For scaling concurrency, Python has limitations due to the GIL, Global Interpreter Lock, which make multi-threading not always speed up CPU-bound tasks. But for I/O-bound tasks, like reading files, waiting for network, threads or asyncio can help. For CPU-bound, using multiprocessing or joblib to spawn multiple processes or offloading to native code, C extensions, can bypass that. However, don't prematurely optimize. A rule of thumb: make it work, then make it right, clean, tested, then make it fast if needed. Ensure the design is flexible enough to change the internals for performance without breaking the outward API. Engaging analogy for best practices: writing code is like gardening. Without structure and care, it can grow into a wild, unmanageable thicket of weeds. But by pruning, organizing, sectioning the garden into beds, and maintaining, weeding, checking plant health, you get a flourishing but orderly garden. Modular design is like having separate beds for different plants, vegetables in one, flowers in another. Readability is labeling each plant and keeping paths clear so you can walk through without tripping. Version control is keeping a garden journal, knowing what you planted where and when, and being able to undo a change. Like if a certain fertilizer killed a plant, you roll back to a previous state. Scaling is expanding the garden. Maybe you acquire more land. You need a consistent plan so the new sections integrate well with the old, and perhaps stronger tools to manage a larger area. In line with RBY metaphor: red, structure; blue, style; yellow, tools like version control, combine to produce a bright, maintainable project. And consistent with A equals C equals 1. Loosely speaking, the idea is that by following best practices, the codebase remains one cohesive whole, even as many pieces evolve. Everything in balance and unity, rather than chaotic disarray. From a source standpoint, an expert summary says, high-quality code is functional, readable, maintainable, efficient, and secure. You can achieve these qualities by following best practices such as descriptive naming, consistent coding style, modular design, and robust error handling. Asterisk. It also emphasizes that clear naming, modular design, and testing are key. This aligns perfectly with what we've discussed. 11.6 Continuous learning. Finally, keep learning and iterating. The tech world, especially AI, moves fast. New libraries, new techniques come out frequently. Python itself updates, though it's quite stable in terms of not breaking backwards compatibility often. Be active in reading docs, joining communities like forums or local meetups, and maybe contributing to open source projects to sharpen your skills. And remember, the path to mastery is a recursive process too. Build, get feedback, from errors, from peers, from results, improve, and loop again. Cite. Writing quality code in Python involves clear naming, modular design, and adhering to standards like PEP 8 for readability. These practices result in code that's easier to maintain and scale. Following a consistent style and using tools, linters, formatters, can automatically help enforce readability. Conclusion. Your ongoing journey in Python and AI narrator, reflective, encouraging tone, congratulations. We've traveled from the very basics of Python, setting variables and writing simple loops, to the lofty ideas of AI pipelines, HPC clusters, and AI-assisted coding. It's been a comprehensive tour, and if your head is spinning a bit, that's okay. Let's take a moment to appreciate how far we've come. You started with no prior programming experience, and now you have a mental framework for writing and understanding fundamental Python code structures. Organizing code into functions, classes, and modules for clarity and reuse. Handling errors gracefully and using traceback information to debug, turning errors from roadblocks into learning opportunities. Conceptualizing the steps needed to build real-world AI systems, data to model to deployment to iteration, and knowing that Python is the thread connecting those steps. Considering the infrastructure side, like HPC, when scaling those systems up, and recognizing that Python can scale with you, as the coordinator or even the workhorse, in those environments. Using large AI models, LLMs, as partners in development, while applying critical thinking and verification to their outputs. Embracing best practices that will make your code not just a one-off script, but a living, growing project that can be maintained and expanded over time. Think back to those conceptual frameworks you hold dear. A=C=1, RBY theory, recursive singularity logic. They were our creative companions in this narrative. We saw how combining primary pieces, be it primary colors or primary coding constructs, yields complex results. We saw unity in how code components come together into one functioning program. We saw loops and feedback in learning, both in how you debug code and how AI models are improved, a nod to recursive self-improvement. While these metaphors might have been lighthearted, I hope they made the abstract concepts a bit more tangible and memorable. After all, programming is both a logical discipline and a creative one. You are literally creating something from an idea, much like an artist or writer, but with the medium of code. As you continue, remember that mastery comes with practice. Listen to code, speak code. Yes, talking through code logic can help solidify understanding, and above all, write code. Start small projects. Maybe a simple text-based game, a personal data analysis, or a mini web scraper. Gradually, try out a machine learning project. Perhaps train a simple classifier on a dataset that interests you. Use the pipeline mindset. Get data, write pre-processing steps, try a model, evaluate it. You'll find that each time, the process becomes a bit clearer and you might even automate parts, writing scripts to do repetitive steps, essentially building your own pipeline. Don't be afraid to return to these chapters. Sometimes revisiting a concept after trying it out makes the pieces click in new ways. And keep that sense of wonder and creativity. It's something not every engineer remembers to do, but it will serve you well. Draw analogies, imagine narratives. It's not silly if it helps you understand and remember. Programming is often taught as pure logic, but there's room for imagination in how you grasp it. One day, you might be building those complex AI systems of your dreams, perhaps using Python to weave together data streams, machine learning models, and interactive AI components on a global HPC platform. When that day comes, pause for a moment and realize, under the hood, it's the same fundamentals you learned here, just scaled up, layered, and executed with precision. The little building blocks, variables, loops, functions, they empower the big systems. So keep this guide as a map, but don't forget to enjoy the journey itself. There's a joy in solving problems with code, akin to solving puzzles or crafting something with your hands, and also a joy in knowing those solutions might help people or achieve something significant, like a model that helps diagnose diseases, or an automation that saves time. Narrator, smiling voice. I'll leave you with a bit of the Zen of Python, a poem of aphorisms that Python programmers often refer to. You can even see it by typing import this in a Python interpreter. 2 lines from it say, in the face of ambiguity, refuse the temptation to guess, and now is better than never. The first reminds you to write code that's clear, for yourself and others. We've emphasized that with readability and explicitness. The second urges you to dive in and try. Don't wait forever thinking you're not ready to build that project or automate that task. Start coding, experiment, and learn from doing. Your adventure in Python and AI is just beginning. Keep coding, stay curious, and perhaps soon your scripts and systems will be running on that grand AIOSIO global HPC, turning your innovative ideas, maybe even based on those unique theories of yours, into reality. Happy coding and bon voyage on your programming journey. Sources in this guide provided factual information and best practices. Python's clear syntax aids learning. AI pipelines cover data ingestion through model deployment. Structured code with modules and clear imports improves maintainability. Handling exceptions using try, except and reading tracebacks is crucial. LLMs can generate but require verification of code, and writing high-quality code entails clear naming, modular design, and adherence to style standards. These principles and examples have been woven into the narrative to ensure accuracy and reliability as you learn.